right, students, let's work on this lesson. This is on divergent plate boundary. All right, copy down your teaching point. I'll be able to explain how divergent plate boundaries create features on the ocean floor, such as mid-ocean ridges and rift valleys. Launch for this lesson, turn to page 12 of your reference table and examine the map. Identify and highlight the areas where you think divergent plate boundaries might be located. Discuss your reasoning with your partner. Now, we're not in class, so if you want to just think of an answer yourself. That's it, right? Otherwise, it might be a little difficult understanding why you might be talking to other people. All right, so for your reference table, page number, oh, that's not it. All right, page number 12. We want diverging plate boundaries. Come over here to the bottom left. Right here is your divergent plate boundary. We have some, like a nice bold line, right? And by the bold lines, we have some arrows that move apart. Right. In addition, we have total spreading rate in centimeters per year. Directions are approximate. So we have the arrows moving apart, which represents a divergent plate boundary, and it's spreading at a rate of 7.4 centimeters per year. So a great example of this, right, would be your Mid-Atlantic Ridge. We can see those bold lines there, kind of like a little zigzag pattern. All right, I'll explain to you what that means in a few minutes. All right, kind of goes down to here, to this point, and then we have more of a divergent plate boundary in that direction, more of a divergent plate boundary in that direction. Not every ridge is named, but this is one big one. Mid-Atlantic Ridge, Mid-Atlantic Ridge. All right, it kind of goes up to maybe like around this point here. All right, so the Reykjanes Ridge is up here by Iceland. Right, that's what they call that area where there is separation. So between the North American plate and the European plate, looks like we are having a spreading rate of 2.8 centimeters per year, 2.5. A little bit further south, right, going into the southern hemisphere, we have a rate of 3.8 and a rate of 4. So we have a greater rate here in the southern hemisphere portion of the Mid-Atlantic Ridge. So we might have more magma pushing on these plates a little bit more than the areas up north. All right, so that's some areas where we have divergent plate boundaries. We also have them over here in the Indian Ocean. All right, we have the Indian Australian plate, which is part of Australia and New Zealand too. All right, so Australia and India together. And there is a ridge kind of running southward around where India is located. Right, the old reference table called this the Mid-Indian Ridge, but there's no name here. Then we have the Southwest Indian Ridge. We have the Southeast Indian Ridge. And these are going at faster rates. Look at 7.4 and 7.4 for the Southeast Indian Ridge. That's a bit faster. 1.6 here, Southwest Indian Ridge, not moving as fast. 4.9, pretty fast. And 2.7, not as fast as the 4.9 and the 7.4s. Other locations we have, if you go on the other side of the Pacific, right near our western side, We have a plate boundary here for a ocean ridge, and this is a small plate called the Juan de Fuca plate. And this Juan de Fuca plate is very important, especially with some natural disasters that can occur by the northwestern section of United States. States like Washington State, Oregon, and maybe Northern California, big concerns. And a lot of California here too. All right, down by the Cocos Plate, we have more of divergence. East Pacific rise, right? That is more divergence happening there. Right, we have the Chile Ridge. Excuse me. All right, so we have a lot of these scattered all around. Right, so where we find these, where the arrows moving apart. Oh, let's do this too. You go page before, page 11. All right, the divergence is happening over here on this side. We have the ocean ridge, mid-ocean ridge. We have one here. It looks like there's one over here as well. And that's where the plates are moving apart, just like how it is on page 12. So this plate is moving here, right, to the left in this image. This plate over here on this side of the ridge is moving toward the right. Same thing over here. We have an offset ridge. It's offset. So this portion is moving to the left. And then if this is the ridge, right, across here, this portion is moving to the right. You have many of these offset ridges, and they're all around here too. The key is showing you some offset ridges. It's not continuous. Here you have a bold line, here's another bold line, and it's offset, and that's the offsetting. Here and here, right, it's not continuous, it's offset. This line and this line, it's not continuous, it's been offset. Same thing here, this line and that line, it's not continuous, it has been offset. All right, here we go. Divergent plate boundary. A boundary where two tectonic plates move away from each other. All right, this usually occurs along the ocean floor, and sometimes this can happen on land, right? And that's my next slide. We have tectonic plates. We have a large, rigid piece of the Earth's lithosphere that moves over a semi-solid asthenosphere. And it's highlighted here, right? This area is your divergent plate boundary. We have our tectonic plates. We have many tectonic plates on your reference table. All right, like for instance, right, we live on the North American plate. There's another big plate south of us called the South American plate. We have smaller plates like the Caribbean plate and the Cocos plate and the Juan de Fuca plate. We have a big plate, the Pacific plate. Another big one, the African plate. Another really big one, the Eurasian plate, Europe and Asia together. Small plate, Philippine plate. The Caroline plate, that's new. The Fiji plate, that's a small plate. The Sandwich plate, no pun intended there. Scotia plate, another smaller plate. Arabian plate. So we have big plates, we have small plates, the Indian Australian plate, another big plate. All right, and these plates will move along the ocean floor away from each other. And this is due to your asthenosphere. Now, the asthenosphere is part of your mantle, and it's part of the upper mantle from page number 11 of your reference table. Now, the word asthenosphere is not on there, but you're kind of expected to know now that the upper mantle is known as the asthenosphere. That is semi-solid or a soft solid rock. All right, next, rift valleys. A low-lying area formed when the Earth's crust pulls apart at divergent plate boundary, causing land between the separating plates to sink. All right, so that's a great example here. So we have a rift valley in this picture. This is a nice cross-sectional picture of that. We have the splitting of the Earth, right? This plate here is moving to the left. This one is moving to the right. And this is producing a rift valley where portions of the plate can begin to sink, and we have these blocks that can move down. And it looks like the lowermost portion of these blocks that are breaking apart is where the magma from the asthenosphere is moving up into the lithosphere. And as the Earth is moving apart, this magma is coming in to fill in its place. So it has to cool down, it has to solidify, and it makes your igneous rocks. All right, this happens both on land and in the ocean. All right, and it happens to be on land here over the continent of Africa. This is known, it used to be on the old reference table, not in this one. This was named the East African Rift. So Africa is breaking apart. If this continues to happen, right, if you think about it, South America and Africa was once together and it broke apart. And what formed between them? Currently, what formed between them now is water. So if this continues to happen, water can eventually come in, ocean water coming in, and can fill in that area if it continues to break apart and if it's low enough below sea level. All right, fracture. Remember this. Fractures are rocks that can break. So fracture zones, cracks or faults that offset the ridge. So these are all of your fractures, right? Here's a fracture, here's a fracture, right? It's breaking apart into these blocks. All right, other things, topography, the shape and features of the Earth's surface, such as mountains, valleys, and plains. All right, so that's a word. In our first unit, before we changed to the new NGSS standards, we used to have our first unit as being size and shape and topography of the land. We no longer have that because it's not in NGSS anymore, although it may pop up on your regents. But topography is this: the shape and features of the Earth's surface, such as mountains, valleys, and plains. We have topography on land, and we have topography below sea level, right? It's rock. They are formations, but they're just submerged under sea level. That's what it is. So under sea level, we have mid-ocean ridges. You already have that definition, right? Those are your elongated mountain ranges where you have the Earth splitting apart. We have hydrothermal vents, right? Those are basically openings in the Earth where hot material can basically spew out, right? I have here emerge, right? Spewing out. So superheated water from hot rock underneath, right? And minerals that can be melted will be shooting out into the ocean, making the ocean very saline or even more saline than usual. But these are at the great depths of the ocean. It will take a lot of the spewing out of these minerals to significantly change the salinity of the ocean. All right, last one, seamounts. All right, so seamounts are like mountains, but a little different. All right, so seamounts, an underwater mountain formed by volcanic activity. So they are volcanically active. That does not reach the ocean surface. So they're submerged, kind of like that. All right, so hydrothermal vents. All right, so these are going to be kind of like these volcanoes that, or vents in the ocean that will shoot out the hot material. All right, and then we have seamounts. All right, and seamounts are underwater mountains that are volcanically active. Right, they're underwater. We have a whole bunch of seamounts. Seamounts in the Pacific Ocean. Yeah, it's called the Emperor Seamounts. So we have a chain of. I need to teach you some hot spots, but Hawaii is a hot spot. That's a little different from what we're doing now, totally. But there is, after the island of Kauai, you have a whole bunch of seamounts, right? They're underneath, they're under sea level, and there's more of them in this direction called the Emperor Seamounts. They were once active, but now they're not. Some of these can be broken down to the point where they're officially under sea level. All right, moving on from that. All right, how the features form. We have magma rises. Magma will always rise because magma is in liquid form. And in terms of densities, right, for most materials, excluding water, liquids will rise. It's less dense than the surrounding rock, which is going to be solid or solid-like. So solids are more dense, liquids are not, right? So liquids will begin to rise. So in this picture here, we have the rising of magma. It's less dense. Once it gets toward the surface at your mid-ocean ridge, right, it's going to cool down and forms new oceanic crust. And this new crust will be a type of igneous rock. And the classification of this rock is going to be extrusive. All right. Repeated eruptions build a ridge and form valleys. All right. So valleys are going to be some of the lower portions, right, of the Rift Valley in that previous picture. Another important thing here is a new type of plate boundary that exists when you have an offset of your mid-ocean ridge. Here is a mid-ocean ridge. Here is a mid-ocean ridge. This side is going to the left. This side is also going to the left. This side is going to the right. This side is also going to the right. Right, but the main thing here is that when you have overlap, one plate will slide past the other. And that sliding will result in a transform fault boundary. So we have a whole bunch of these all over the place on page 12. Those are your offset mid-ocean ridges. All right, there you go. Offset ridges on the ocean floor result in another type of plate boundary called a transform fault boundary. There you go. All right, you can, if you need that, need more time, you can pause this video at any point in time. All right, and that's it. All right, going back to page number 12. All right, here is a great example. All right, so you have a ridge here and a ridge here. These two ridges are offset. And this line here that kind of connects them is a transform fault boundary. Right, here's a ridge, here's another ridge. They're offset. This line here kind of connects them through a transform fault boundary. Some of these are pretty long, like this is pretty long. Here is a ridge, here's another ridge, and then here is the transform fault between those two offset ridges. Some of them are pretty close. Let's see. All right, like, maybe like these two are kind of close. All right, I'm going to post the link to work on some questions if you want to on this lesson. Please get to it, right? Try them out. I think I have a few drawing questions on there for you. All right, thank you. All right, guys, have a good night. Or have a good day.